Hello everyone, so this is the final video of those electromagnetism videos. It's transformers. Now I'm only going to do one. I'm going to do the step up transformer and then you can try and apply it to the step down. Okay, so for transformers what we need to make sure we've got is this core material. So this would be an iron core, iron being a magnetic material. And then on the left hand side here, what I'm doing is going to put my input. So I'm going to have a wire coming round, and then it's going to coil around this core just 3 times here. And I'm going to draw this symbol here to represent AC, alternating current. I'm going to come back to this in a minute. It's very important that you remember that it's AC for a transformer. Now on the output, I'm going to draw a few more coils. Okay, so that side that I've drawn now has got more turns on the coil. So this left-hand side, the input, we label as the primary coil. And that will have a number of turns, N, and we put a little subscript P to indicate that that's the primary coil. This will also have a potential difference across it, an alternating potential difference of VP, so voltage primary. And this side, we've got our secondary coil. And again, this is going to have a number of turns, NS, and it's going to have a potential difference across it, VS. I'm just going to rub this iron core out so I can write the step-by-step explanation of how it works. So the first thing to write is that there is an alternating current in primary coil. Now, if you've got an alternating current in the primary coil, we know from our previous videos that whenever you've got a current flowing in a wire, you induce a magnetic field. So number 2 is that an alternating magnetic field, I'm just going to write mag field, is induced around the wire, but also because iron is a magnetic material, it's going to be induced in that core, induced in core. Now, because it's an alternating current producing an alternating magnetic field, I want you to think about the magnetic field in this core kind of going one way, then the other way, one way, then the other way. And what that does is, what that means is that this secondary coil experiences a changing magnetic field. So in effect, these coils are cutting that field line over and over and over and over again. So that third point is going to be that the secondary coil experiences a changing or an alternating, I'm just going to mix it up a bit, changing mag field. And we know that when that happens and field lines are cut, an alternating PD for potential difference is induced in secondary coil. So they're the step-by-step instructions, and they pretty much apply for the step up and the step down. The reason this is a step up is because if you were to count NP here, the number of turns on this coil, well, that's less than the number of turns on the secondary. So the final step in this would be to say that a larger potential difference is induced in that secondary. If it was a step down, you'd have more turns here, less turns there. So you can almost think about the right-hand side being your input, the left-hand side being your output. Because there's less turns, you'd get a lower potential difference. So step up and step down refer to what's happening to the potential difference. If I just turn over and deal with the equations, sorry, the board's a bit messy. So there are 2 equations that are given, and if you take the ratio of your number of turns on your primary to your number of turns on your secondary, that will equal the ratio, silly sausage, that will equal the ratio of your potential differences on your primary to your secondary. Now there's another thing we need to consider, and that's the conservation of energy. So there is actually a power on the primary coil, IPVP, and we know that energy is conserved, and if we write the equation for energy, energy is power times time. Well, this stuff is all happening at the same time, so power is energy over time. That means that power is going to be the same on the primary and the secondary, in an ideal world. In reality, you'll have some energy transferred to the surroundings, some heat losses, so the power is always going to be less on the secondary anyway. But this equation here, this indicates that the power on the primary is going to equal the power on the secondary. Okay, so examples including these, they'll give you obviously 3 of the variables. You've got to work out the missing one, but just try to remember that n is the number of turns. So you've got NP, NS. The subscript P is primary coil, and the subscript S is the secondary coil. So if we just do a quick example, let's say I had 230 turns on my primary, and I wanted to know how many turns on my secondary, and I had an input potential difference of 200, and I had an output potential difference of 200,000. Okay, so we can see that this ratio on the right hand side is got to equal the ratio on the left hand side. Now, because I want NS and it's on the bottom, a little trick you can do is just flip both sides. So I'm going to write NS over 230 equals 200,000 divided by 200. So obviously, NS, I'm going to mark space a bit here, NS over 230 is going to equal 1,000, because that right hand side is equal to 1,000. And now, if I want to get NS, I can just multiply 1,000 by 230, so NS is going to be 230,000 turns. Okay, and this one I find is a little bit easier because it's not the ratios, but if you want some more examples of that, I can do that. Okay.